Okay, in this video I'm going to go over the free response questions. This is 2001 number 4, 2002 number 2 and 3, 2004 number 2, and 2005 number 1. So in 2001 number 4 you see an experiment involving a forest, and the forest has trees on the left side there to the west. And we look at blocking scheme A and blocking scheme B. And so you want to look at which one is better. So like which one, meaning which one should be, how should we block them, how should we separate them. Now I will look at it actually does say that blocking scheme A is the best. Now so think about why you would want all four right there on the left and then the other block of 4 on the right. So think about why A is the best and explain your answer on that. For part B, why would you need to, so now that you've blocked it and you've got 4 spots to put the 4 different types of 2 of each of the 2 varieties of trees in there, why would you need to randomly assign them in those 4 spots? So what other factors could be taking place that would make you want to just randomly put them in there and not just say, okay, we'll put it here, 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 and here? Why would you have to randomly do it again and make sure that you would do that? Okay, that takes care of 2001 number 4. It's pretty quick. So then we move to 2002 number 2. It says a manufacturer of boots plans to conduct an experiment to compare a new method of waterproofing to the current method. The appearance of boots is not changed by either method. The company recruits 100 volunteers in Seattle, where it rains frequently, to wear the boots as they normally would for 6 months. At the end of 6 months, the boots will be returned to the company to be evaluated for water damage. So they want to see if the waterproofing of these boots is better. Describe a design for this experiment that uses the 100 volunteers. So again, you're going to take 100 volunteers, and how would you design it? Now, to design a good experiment, remember, you're going to have to assign them to two groups. But think about, how could you assign one person to both groups? So I want you to think about that. That would be the best design, probably, is how could you design it one person to each group. And again, how you do that would be is up to you, but that's what you want to be able to do. Now, could your design be double blind? That means would the person giving them the boots and the person receiving the boots not know which ones they were getting? So is that possible in this experiment? Alright, we go to number 3. Number 3 shows you the mean and standard deviation. If you remember a normal curve, you can remember what the probability is of being 1 standard deviation away, 2 standard deviations away, and so on. In A, runner 3, who has a mean of 4.5 and a standard deviation of 0.14, thinks that he can run a mile in less than 4.2 minutes. How likely is that to happen? So how many standard deviations away from the mean is that? So that makes that how likely to happen. And you can explain why it's not likely or why it is. The distribution of team times is approximately normal. That means we can add up the means and get the average of that for the whole team, and we can add the standard deviations and get the average of that for the whole team. So what are the mean and standard deviation of the teams? And that would be an easy way to do. And then the next one, as we go to, let me get there. Okay, as we go to the next part C, suppose the team's best time is 18.4 minutes. So that's the best they've ever done. What's the probability that they could beat their own best time in the next race? So what's the probability that they can get less than 18.4? So basically you find the z-score of 18.4 compared to the mean, and then what's the probability that it would be less than that? So again, normal CDF, negative 999 to that z-score. Same thing in A, when you get how many standard deviations away 4.2 is for runner 3, you'll do a normal CDF of negative 999 to 4.2. That tells you how likely he is to run the race in 4.2. Okay, we go to 2004, number 2. In the first one, so you've got a formula, you've got 12 volunteers who participate, gives you their gender and their age, and we want to compare the condition of hair for people who use the new formula and people who use the current formula. These researchers want to conduct an experiment involving the two formulas, new and current. They believe the condition of hair changes with age but not gender. So they don't think the gender is important, but they do think that the age is important. Because researchers want the size of their blocks to be equal to the number of treatments, they're going to use blocks of size 2 in their experiment. That would be included in each of the 6 blocks, and give the criteria you use. So basically, they want you to separate these 12 people into 6 groups, 2 of each, based on age. So how could you do that? What volunteers would be in the first group? What would be in the second? What volunteers would be in the third? What volunteers would be in the fourth? What volunteers would be in the 5th group? And what would be in the 6th? And do it based on age. Okay, in part B, the researchers believe that hair condition differs with both age and gender. Again, they want to use groups of size 2. So how can you block them? So basically, they want a female group that's young, who would be in that one, a female group that's medium age, a female group that's old. Then they want a male group that's young, a male group that's medium age, and a male group that's old. So again, which volunteers would be in each one? That would be your 6. Okay, C says the researchers in Part B decide to select 3 of the blocks to receive the new formula and to give another 3 blocks the current formula. Is there an appropriate way to do this, to assign the treatments? If so, describe a treatment. If not, explain an appropriate method for assigning the treatments. So how could you pick which 3 that you would give the new treatment and which 3 you would give the old treatment? Or is this just a bad experiment, and why is it a bad experiment? Okay, we go to 2005, number 1. Again, this is a question 1, so it shouldn't be too hard. In part A, you want to compare the 2 distributions, your socks, shape, outlier, center spread. Part B, is it reasonable to generalize the findings of this study to all rural and urban 9th grade students in the United States? So this study was a sample of 9th grade students from one high school in a rural area. So can we generalize that to the entire United States from one high school? Why or why not? And you must explain fully in these. Part C, researchers want to conduct a similar study. They're debating which of the following 2 plans to use. Plan 1 would be have each student in the study record all the food he or she consumed in a day, and then researchers would compute the number of calories of food per body weight for each student. Plan 2 is have each student record all the food they consumed over a 7-day period. Then researchers would compute the average body weight of the average calories consumed with body weight during that 7-day period. Assuming that the students do keep accurate records of the food they eat and everything, which would be better, plan 1 or 2? And which would meet the goal of the study better? And justify your answer. So would you do plan 1 of how much you ate in 1 day, or should you use plan 2 where you use 7 days? And why would you pick one plan over the other? So that takes you through those AP free response questions, kind of guide you. I didn't give you any answers, but I've kind of guided you through the process. You should be thinking on those. If you'll finish all that, and we'll go over them briefly in class, but you will be turning those in. So that will get you started on experiments, which are a big part of the cumulative test, so it continues to keep you thinking of those as we move forward in this class. All right, thank you.